Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Today's topic of discussion is the check valve. Our objective is to introduce check valves and discuss their purpose, construction, method of operation, and application in fluid power systems. Additionally, we'll examine restriction type, pilot to open, and pilot to close check valves. Valves are devices within fluid power systems used to control direction, flow rate, and pressure. The check valve is a valve that selectively blocks fluid flow in one direction and allows fluid flow in another. As we'll learn, this selective passage of fluid can be used for a number of applications. Since this is an early lecture in this sequence, let's discuss terminology commonly applied to most valves. Not all valves have all these features, but this does serve as a pretty good introduction to all things valve for right now. Later lectures will detail the features we don't examine today when it's appropriate to do so. For now, consider this a general orientation, after which we'll examine the check valve and apply these terms. First, valves have a valve body, which is a housing for the internal valve components. Additionally, a valve has ports or ways, which are the entry or exit points for fluid, the internal passageways of the valve. Some valves have movable parts like spools or poppets that selectively stop, start, or change direction of fluid flow or modify flow rate or pressure. A poppet, for lack of a better descriptive term, are kind of like plugs. Spools, in contrast, are cylindrical devices with lands and valleys that selectively connect or disconnect the internal passageways of the valve. Poppets and spools may include seals like O-rings to prevent leakage. Some valves include fixed or adjustable springs used to bias, center, or offset the movable components. Finally, some valves include actuation and adjustment methods that allow the valve to be placed in different positions or change the biasing force of a spring. Additionally, valves can be categorized by their mounting method. Valves can be inline, subplate, manifold, cartridge, or stack mounted. An inline valve is quite literally placed in line and directly attached to fluid conductors like pipes and hoses. While inexpensive, any repair or replacement involving an inline valve comes with the ever-present possibility of dorking up the threads, bending, twisting, or breaking the directly attached fluid conductors, or distorting the valve body and causing annoying leaks or catastrophic failures. In contrast, a subplate-mounted valve uses a machined subplate directly attached to system plumbing, and the valve is then attached to the subplate with threaded connections. O-rings and/or gaskets prevent leaks between the matching valve and subplate ports. Standardized size of subplates and valves allow quick interchangeability. A technician will lock out and tag out the system, remove a couple screws, pop off the old valve, pop on a new one, tighten a couple screws, and return the system to service, all without causing more problems. The old subplate mounted valve can be repaired or rebuilt and returned to stock. Manifolds, if you think about it, are kind of like large subplates to which a number of valves can be externally attached. The manifold is a machined metal block into which internal passages are drilled. The manifold is in effect a common circuit free of potential leaks associated with external plumbing. In contrast, cartridge valves screw or slip into passageways drilled into the manifold. Cartridge valves are compact and easily removed and replaced. Finally, stack valves use a mounting style similar to subplate mounted valves, with the exception that a stack valve is intended to mount directly to another valve rather than a subplate, the top valve in a tower being the notable exception. The connected passageways within a tower of stack valves therefore save space, reduce the possibility of leaks, and eliminate the need for external piping. Within a larger system, a combination of these mounting methods can be used. Connections from a hydraulic power unit can be routed to a manifold containing a number of cartridge valves. Then, via flexible hoses or rigid pipes, fluid can be routed from the manifold to subplate-mounted valves, a collection of stack valves mounted on a subplate, or other inline valves, all controlling the strength, speed, and direction of fluid power actuators. Returning to the intended topic of this lecture, check valves are extremely simple valves. The cutaway view of a basic check valve shows a movable poppet that fits into a seat machined into the valve body. The movable poppet may or may not be held in place with a light biasing spring. When fluid enters in this direction, it overcomes the light biasing force of the spring and pushes the poppet off the seat, and fluid flows freely. In contrast, when fluid enters in the opposite direction, it forces the poppet onto the seat, and fluid flow stops. Terminology differs from manufacturer to manufacturer. However, the direction of free flow dictates which port is assigned which identifier. The inlet can be called the primary or P port. The outlet can be called the secondary or A port. Check valves often indicate the direction of free flow by scribing an arrow on the side of the valve body. The inscribed arrow is less likely to fall off than a sticker and remains readable when painted over. Don't laugh. This happens more often than it should. The schematic symbol for a check valve shows a ball on a seat because old school check valves really did use a ball rather than a poppet. The ball fell out of favor because over time, the ball would wear a groove in the seat and would function perfectly well until someone took it apart. If the individual responsible for reassembly failed to put the ball perfectly back into the groove, the check valve wouldn't seat properly and allow a degree of leakage in the ordinarily blocked direction. For this reason, most check valves employ a self-guided poppet that easily seals even after reassembly. Regardless, the schematic symbol still uses the ball and seat symbol. Schematically, free flow pushes the ball off the seat, block flow pushes the ball onto the seat. Note in the free flow direction, fluid must overcome the force of a light biasing spring. This implies a check valve in the free flow direction isn't exactly free and necessitates a little push. This initial push is known as cracking pressure and is the pressure at which the poppet partially unseats. Most check valves have extremely low cracking pressures, on the order of 5 psi. At the full open pressure, the poppet fully unseats and allows unrestricted flow. The region between cracking pressure to full open pressure would see increasing flow in the free flow direction as the poppet progressively unseats. Consider, however, a check valve with an extremely heavy bias spring, employed as an especially primitive pressure relief valve. For example, consider a check valve with a heavy bias spring and a cracking pressure of 700 psi and a full open pressure of 800 psi. Up to 700 psi, even the free flow direction of the check valve remains closed, and flow rate through it is 0 gallons per minute. However, when pressure hits 700 psi, the poppet ever so slightly cracks open and diverts a small portion of the provided flow to the tank. As pressure rises from 700 to 800 psi, the poppet opens more and more and diverts an increasing portion of flow to the tank. Finally, when pressure hits 800 psi, the check valve fully opens and diverts all flow to tank. This system is therefore limited to a maximum pressure of 800 psi. While effective, this primitive means of pressure relief isn't exactly the most elegant of methods, principally because of the large differential between cracking and full open pressure inherent to the direct acting nature of this primitive pressure relief valve. We'll examine more sophisticated pilot-operated pressure relief valves in later lectures that overcome this difficulty. Sophisticated, by the way, is a euphemism for more complicated. You'll notice, even for a check valve with a light biasing spring, that unrestricted free flow isn't exactly what I would consider unrestricted, since the poppet still remains the path of flowing fluid like one of those large waddling beasts or slowly ambling cell phone users that insist on taking up the center of a narrow hallway or sidewalk in the middle of rush hour. Free-flowing fluid is forced around the poppet, contributing to turbulent flow, resultant pressure drop, heat, noise, and inefficiency. For this reason, consider an alternate arrangement of a basic check valve called a right-angle check valve. In this case, fluid flow is still blocked from out to in. However, when flow is routed in to out, the poppet is forced out of the path. Free-flowing fluid still has to make a hard 90-degree turn, but it sure beats zigzagging around an obstruction directly in the path. Another type of check valve you may run across is something known as a restriction or orifice type check valve. This type of check valve is designed to purposely leak in the block direction. Upon first consideration, this might seem like an extraordinarily stupid idea. However, it does have its uses. First, the leak in the ordinarily blocked direction isn't uncontrolled, but rather a measurable, predictable quantity. The restriction type check valve is therefore a means of flow control. Flow rate, if you'll recall, is the principal means a fluid power system uses to influence the speed of a fluid power actuator. A restriction type check valve can therefore allow full speed actuation in one direction by allowing full unrestricted free flow, yet allow reduced speed actuation in the other direction by allowing only a measurable quantity of fluid to pass. A restriction type check valve is basically a regular poppet style check valve with a tiny orifice drilled through the poppet. When fluid enters in the free flow direction, the full poppet is pushed off the seat and fluid flows freely. When fluid enters in the restricted flow direction, the poppet is pushed onto the seat and fluid is forced to travel through the tiny orifice. Given a smaller orifice, only a smaller quantity of fluid can negotiate the narrow path in the same time. Both flow rate and actuator speed are therefore reduced when the restriction type check valve conducts metered flow in the restricted direction. The schematic symbol for a restriction type check valve shows a regular check valve with a fixed restriction drilled through the center of the ball. Free flow pushes the ball off the seat. In contrast, restricted flow pushes the ball onto the seat and is forced to negotiate the tiny passage. It should be noted that even regular check valves exhibit a quantity of leakage in the block position, especially with low viscosity or thin liquids at high pressures. Let me briefly introduce two more types of check valves before we discuss some basic check valve applications. The previously discussed check valves were direct acting, and that fluid directly acts on the poppet face. Consider, however, a pilot to open check valve that, in addition to direct action on the poppet, receives a pilot pressure signal X from somewhere else in the system. The cutaway view shows the cap end of a piston receiving the pilot signal X. The piston is linked to the check valve poppet via a connecting rod. Note, in this configuration, the primary passage and pilot sections are not connected, but only interact via the connecting rod. In the absence of pilot pressure, the pilot open check valve acts just like a regular check valve. In the free flow direction, the poppet is forced off its seat, and fluid flows unrestricted through the valve. In the blocked position, the poppet is forced onto the seat, and fluid flow stops. This behavior radically changes, however, in the presence of a pilot signal.